To get started, we're going to look at a general scheme for solving Maxflow min-cut problems known as the Ford-Fulkerson algorithm. Dates back to the 1950s. The idea is to start with no flow anywhere. So we initialize all edges to have capacity 0. And then find any path from S to T so that you can increase the flow along that path. Now the simplest case is when the edges all go in the same direction from source to target. We'll look at the other case in a minute. In that case, so there's a path, and this is a general algorithm. It works for any path. If there's a path from S to T, go ahead and find it. And if there's capacity left in each one of the edges, if none of them are full, then what we want to do is augment the flow along that path. So we put as much flow as we can through that path. In this case, we can put 10 units of flow through each path, through each edge. There's room to put 10, and 2 of the edges fill up in that case. But we've increased the flow in the network by 10 in that case. And the algorithm is just continue in that way, finding a path. So here's another path. And this one also, the edges all flow from source to target. And in this case, again, we can add 10 more units of flow because the last edge only has capacity 10. So load up those edges with that flow, and now we've got 20 units of flow in the network. Notice when we augment along an edge, we're preserving the vertex equilibrium, local equilibrium at a vertex property. We're putting some flow in and taking the same amount of flow out. So here's another augmenting path. Now this one has what's called a backward edge. So notice that the path going from S to T goes backwards along that edge. And the idea is that you can augment flow through the whole network by removing flow in that path. That is, if we add 5 units of flow from S to this vertex and 5 units of flow from S to this vertex, then what we can do is remove 5 units of flow along this edge. That's to preserve the local equilibrium. Essentially, that 5 units of flow gets transferred right through. So after we remove 5 units, we add 5 here, that's 5 coming in. We remove 5 here, that's 5 coming in. There's still 10 going out. And then for the forward edges, we add the flow. That is, we can augment the flow along an augmenting path by adding flow to forward edges and subtracting flow from backward edges. The maximum amount of flow that we can push through is the remaining capacity in forward edges and the amount of flow in backward edges. You can't remove more flow than is there. In this case, we can augment the flow in the network by 5. That fills up the first edge. And so now we've got 25 units of flow in the network. And again, the idea of removing flow from a backward edge is very simple. It's just a way to ensure that the local equilibrium condition always remains satisfied as we move along the path. So in this case, there's one more augmenting path. Okay, and that's forward, 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 backwards along that one again, and then forward, forward. So, and then what's the maximum amount we can push through? In this case, this one's got 5 in it, and it's got a capacity of 8, so we can put 3 more units of flow through this network. And we get now we have 28 units of flow going through the network. And the algorithm terminates when there's no way to find an augmenting path from S to T. And what's that mean? That means that every augmenting path, every path from S to T contains either a full forward edge or an empty backwards edge. We can't put more flow through a forward edge, and we can't remove flow from an empty backward edge. When there's no more augmenting paths, the algorithm terminates. And so that's the algorithm. We start with no flow. As long as there's an augmenting path, we find that path and look through the path to find the amount of capacity left in the most full forward edge and the amount of flow left in the most empty backward edge, and we increase the flow on the path by that amount. And if we can't find an augmenting path, we're done. Now there's a few questions about this. So that solves the maximum flow problem. We have to look at how to compute a min-cut. We have to figure out a way to find an augmenting path. That's not too hard. That's similar to many other graph processing problems that we've already solved. And we have to ensure that, or at least show that it always computes a max flow. And there's even a question of, does it actually terminate? Maybe you could get stuck in some kind of situation where it removes flow on an edge in one path and adds it in another. And so even analyzing how many times it does augmentation is actually not so straightforward. So we'll take a look at these questions. That's the Ford-Fulkerson algorithm, a general scheme for solving max flow.